If your electrolyzer voltage rises by just 50 millivolts at scale, you don't lose efficiency, you lose money. In a 100 megawatt hydrogen plant running 8,000 hours per year, a small voltage increase can translate into several additional gigawatt hours of electricity consumed annually. At $50 per megawatt hour, that seemingly minor shift becomes hundreds of thousands, sometimes millions of dollars over the project lifetime. And here's the uncomfortable reality. That voltage rise often has nothing to do with thermodynamic limits. It has nothing to do with catalyst breakthroughs. It has to do with traffic, molecular traffic. Water molecules trying to reach a catalyst surface. Oxygen bubbles trying to leave it. Hydrogen trying not to mix with oxygen across a membrane thinner than a human hair. Hydrogen electrolysis is not just electrochemistry, it is molecular logistics. And molecular logistics define cost. Image 1 shows the polarization curve, the operating fingerprint of an electrolyzer cell. At low current density, the curve rises steeply. This is activation control. The reaction itself requires extra voltage to overcome electrochemical barriers. As current increases, the curve becomes more linear. This is the ohmic region. Voltage increases proportionally with current because the membrane and electrical contacts resist charge flow. Then, at higher current densities, the curve bends sharply upward. This upward bend is the transport ceiling. It is the moment when the reaction could proceed faster, but molecules cannot move fast enough to support it. And that curvature matters economically. Every incremental rise in voltage increases kilowatt hours per kilogram of hydrogen. At scale, that is not academic. It is LCOH. Image 2 shows the internal architecture of a PEM electrolyzer. Water enters the anode flow channels, passes through the porous transport layer, and reaches the catalyst surface. At the catalyst, water splits into oxygen, protons, and electrons. The protons cross the hydrated membrane. The electrons move through the external circuit. Hydrogen forms at the cathode. The reaction itself is extremely fast. Modern catalysts are not the bottleneck. The bottleneck is whether water can physically reach every reaction site at the required rate. Now imagine this happening in a 100 megawatt stack, billions of reaction sites every second. If even a small portion of that surface experiences insufficient hydration, local resistance increases. Resistance increases voltage. Voltage increases energy consumption. Energy consumption increases cost. Microscopic transport becomes macroeconomics. Image 3 focuses on the porous transport layer, the PTL. This is typically sintered titanium, a metallic sponge with interconnected pores. It must deliver liquid water inward while allowing oxygen bubbles to escape outward. At moderate current densities, this balance works. But as current density rises, oxygen generation rate increases proportionally. Bubble formation accelerates. If bubbles form faster than they detach, portions of the catalyst surface become covered by gas. In alkaline systems, bubble coverage has been measured at 30 to 50% at high current densities. Imagine deliberately blocking 40% of your production floor. You would never design that intentionally. But transport stress can create that outcome unintentionally. Image 4 introduces the mass transfer over potential relationship. Rather than reading symbols, notice what the structure tells us. The additional voltage required depends strongly on how close operating current is to the limiting current density. The limiting current density represents the physical maximum before reactant concentration at the catalyst surface becomes insufficient. As operating current approaches that ceiling, the voltage required to sustain reaction rises non-linearly. This is why the polarization curve bends sharply at high current. The equation captures molecular congestion. At 50% of the limiting current density, transport losses are modest. The additional voltage contribution remains small. This is the stable region. This is why many commercial PM electrolyzers operate in this range. There is efficiency, there is margin, there is operational flexibility. Now consider operating at nearly 90% of limiting current. Transport losses increase sharply, but more importantly, the slope becomes steep. Small increases in current produce disproportionately large increases in voltage. Now apply the competitive edge test. If electricity prices spike, which design survives? The one operating near transport ceiling, or the one with headroom? If renewable power fluctuates and the system cycles daily, Which design handles stress better? Aggressive current density reduces stack footprint. Conservative current density preserves efficiency and durability. Under tight capital markets, the design with voltage stability often wins. Bubble coverage intensifies at high current densities. Blocked catalyst area increases activation and transport losses simultaneously. High current density may appear attractive from a CapEx perspective. Fewer cells, smaller footprint. But it increases operational stress. Aggressive design lowers upfront cost. Conservative design lowers lifetime operating risk. In hydrogen markets defined by tight margins, operational stability is a competitive edge. Now consider hydrogen crossover. Hydrogen molecules can diffuse through the membrane to the oxygen side. At low operating currents, oxygen production decreases, but crossover does not decrease proportionally. This creates a safety boundary. If hydrogen concentration in oxygen exceeds roughly 2%, flammability risk emerges. Transport physics now intersects with safety engineering. Crossover flux increases with pressure and decreases with membrane thickness. Pressurized systems reduce downstream compression cost, but higher pressure increases crossover. Thin membranes reduce ohmic resistance, but thin membranes increase crossover. Every design decision shifts another constraint. The molecular flux can be translated into equivalent electrical current. At very low operating loads, such as during renewable intermittency, crossover current becomes a significant fraction of total current. Now consider a solar-powered plant ramping down overnight. If minimum safe current density cannot be maintained, operation must shut down. That reduces annual utilization. Reduced utilization increases fixed cost per kilogram. Transport physics becomes project finance. Theoretical minimum safe current density arises from dilution requirements. There must be sufficient oxygen generation to keep hydrogen concentration below flammability limits. This establishes the lower boundary of the operating window. Now we see something critical. There is a high current ceiling due to mass transfer. There is a low current floor due to crossover safety. The operating window is bounded on both sides. Commercial electrolyzers expand the lower boundary using recombination catalysts. These catalysts convert small amounts of hydrogen and oxygen back into water. This allows operation at lower current densities. But recombination systems add cost, complexity, and maintenance. System simplicity is itself a competitive edge. Returning to the polarization curve, we now see full loss decomposition. Activation dominates at low current. Ohmic resistance governs mid-range efficiency. Mass transfer dominates at high current. Crossover defines the low current safety constraint. This curve defines not just stack physics, but plant economics. Membrane thickness is a trade-off. Thin membranes improve efficiency. Thick membranes improve safety margin. There is no perfect membrane. There is only optimized compromise under specific electricity price, pressure, and utilization assumptions. Image 15 summarizes the operating window. Low current, safety boundary. Mid current, efficiency zone. High current, transport ceiling. Now apply system stress. If utilization drops to 40% due to renewable intermittency, can the system operate safely at low load? If electricity prices spike, can voltage sensitivity remain controlled? If pressure increases to reduce downstream compression cost, does crossover remain manageable? The winners in the hydrogen market will not be those advertising the highest current density. They will be those whose systems remain stable under transport stress, pressure stress, and utilization variability. And this is exactly why systems-level understanding matters. If you are developing, financing, or evaluating hydrogen projects, stack-level performance curves are not enough. You must understand how mass transfer, crossover, membrane thickness, pressure, and utilization interact at plant scale. This is what we analyze inside H2 Hub by Renewable Energy. H2 Hub is not a beginner explainer platform. It is a systems and economics intelligence layer for developers, consultants, and investors who need to stress test hydrogen projects before capital is deployed. Because the difference between a technically functional electrolyzer and a financially survivable hydrogen project often lies in details like the ones we covered today. Molecular transport, operating window boundaries, voltage sensitivity under stress. If you want to go deeper into stack economics, plant-level modeling, and real-world project stress testing, You can explore H2Hub at h2hub.reneweenergy.com.